Hello everyone. Today we are going to look at a very important topic called oxidation of ketones. We know that aldehydes can be easily oxidized, whereas ketones is difficult to oxidize, right? So ketones don't have hydrogen atom attached to carbonyl group, and this is why oxidation of them is very difficult. There is no hydrogen atom over here, so which you can see. So that is the reason why it is difficult for us to oxidize this. Hence, mild oxidizing agents like Tollens reagent, Felling solution, bromine water, they can oxidize only aldehydes, but cannot oxidize ketones. And we exploit this to differentiate between aldehydes and ketones. We know that. Ketones can be oxidized only under vigorous conditions. So I need to use either hot concentrated nitric acid or acidified potassium permanganate or acidified potassium dichromate. So any of this reagent should be used so as to oxidize ketones. So we understood that oxidation of ketones is a difficult process. That's because carbon-carbon bond is going to be broken in during oxidation. So here I have taken a symmetrical ketone. So either this carbon bond or this carbon, either one. Both are similar only. So the breakage of carbon-carbon bond requires more amount of energy, which mild reagents cannot supply. So that's why we require a stronger oxidizing agent to break this carbon-carbon bond, right? So here I'll get two carbon acids like acetic acid plus formic acid. So two acids I will be getting, and this formic acid can undergo one more step of oxidation to give you water plus carbon dioxide, right? But in the case of unsymmetrical ketones, we will get a mixture of products. To find the major product, Popov rule will be helpful, right? This rule states that the carbonyl group will stay preferentially with the smaller alkyl group. So the bond will break like this. Here the bond will break. It states that the carbonyl group will preferentially stays with smaller alkyl group during oxidation of unsymmetrical ketone. So I'll get two carbon acid like acetic acid and three carbon acids like propionic acid. Oxidation with sodium hypohalite. Ketones can be oxidized with sodium hypohalite to get haloforms, and this reaction can be answered only by the ketones that have a methyl keto group, that is CH3 C double bond O. If this compartment is there with the ketones, then such ketones will undergo oxidation with the sodium hypohalite. Now, what is sodium hypohalite? Sodium hypohalite is a compound, is a mild oxidizing agent that can be generated by the action of sodium hydroxide plus any halogens. Halogens here we will consider only chlorine, bromine or iodine. We won't take fluorine because fluorine is very much reactive. It will react with almost everything. So we cannot follow up the reaction. So we will constrain ourselves with the chlorine, bromine and iodine, right? So when I take this, what happens? Sodium hypohalite will be the product along with HX. This is a mild oxidizing agent which will decompose to give me sodium halide plus nascent oxygen, and this nascent oxygen can be used to oxidize, right? Now when we take a ketone that contains methyl keto group, that can be oxidized and the final product will be haloform, right? So CHX3 will be the product. Okay, that's because what happens, this alpha carbon contains 3 hydrogens, when we add 3 moles of sodium hypohalite, these 3 hydrogens will be exchanged for these 3 halogens. So I'll get a CH3 C double bond O CX3. Then OH minus from sodium hydroxide will attack here, so this bond will be broken, and you will get a CX3 which carries negative charge. That will go and attack, take away a proton from this one, Okay, so ultimately I'll get a CHX3. This is the product we will be getting. And if we take a chlorine, then we will get chloroform. If we take bromine, we will get bromoform. Chloroform and bromoform both are colorless liquids. So that is the reason why I prefer iodine, because when I take alkaline solution of iodine, I'll get end up with iodoform CHI3, which is a yellow color solid. So I can easily recognize by the color, and it is used to characterize the methyl keto group better. One more thing, not only this methyl keto group, also this group CH3 CHOH, even the compound contains this compartment, that will also answer iodoform, because this group can be easily oxidized to the methyl keto group, right? So any compounds that contain this group CH3 CHOH group, that will also answer iodoform, which means ethanol will answer, propan 2-ol will answer, and butane 2-ol, whatever, all these compounds will answer iodoform test. Ketones can also be oxidized with nitrous acid. This alpha carbon can be oxidized to acid. So actually nitrous acid is an unstable one at normal room temperature, so it needs to be kept at 0 to 5 degrees Celsius. The best way to prepare is in situ preparation, right? In situ means whenever the situation requires, you can prepare inside the reaction vessel itself. By taking sodium nitrate and HCl at 0 to 5 degrees Celsius, instantaneously nitrous acid will be produced. And when nitrous acid reacts, O double bond N OH. This is the formula of nitrous acid. So when it reacts, 2 hydrogen atom from this alpha hydrogen will go, and I will get a water molecule will be eliminated, and we will get an oxime, right? So we'll get a CH3 C double bond O and a CH, right, double bond NOH. Again a water molecule will be left. Okay, one more water molecule will leave, so I'll end up with a cyanide derivative, which upon hydrolysis will give me the final product, right? Sometimes some different products, unexpected products can also be obtained due to condensation. So the first step is as expected one only. So nitrous acid, oxygen from nitrous acid will join with 2 hydrogens from this alpha hydrogen. So we will get this intermediate. Okay. So C double bond O, CH N OH. Now what happens? This OH will not condense with the this CH group, rather it will condense with another hydrogen from the ring. So a condensation, a new nitrogen carbon bond will form like this, right? So the final product will look like this. CH double bond N, and it will look like this, which is nothing but this product, right? Ketones, when subjected to mild oxidation using peracids, will give esters after undergoing rearrangement, and this reaction is known as Baeyer-Williger oxidation. And the alkyl group which migrates will be attached to oxygen in the final product. So from this we can understand that this oxygen would have been migrated, and that's why this oxygen has been obtained. When we see the next case, we will understand that better, because we have an unsymmetrical ketone. I have a methyl group and an ethyl group. Here ethyl group will preferentially migrate, so that is the reason why methyl group is attached with oxygen. This is an easy way to interpret the product, right? Now when we have that idea and look at the third case, we can understand that this phenyl group has undergone migration, right, because it is attached with oxygen. So the migratory aptitude of Baeyer-Williger is in this order. tertiary will undergo preferentially migration, then secondary, then primary, then methyl group, right? And if you have an aryl group and an alkyl group will preferentially migrate, right? So aryl group will preferentially migrate than alkyl group. This is the next one. And the isomers are the aryl groups having electron releasing group attached to the para position will migrate more preferably than electron withdrawing group attached at the para position. So which means I can say that electron releasing group or electron donating group attached to the para position, such aryl groups will have more migratory aptitude and they will migrate. Fine. So that's all about oxidation of ketones. Thank you, one and all. Happy learning.